silicon with 4 valence electrons, pentavalent impurity with 5 valence electrons, and a trivalent impurity with 3 valence electrons. When a pure semiconductor as silicon is doped by pentavalent impurity, then 4 electrons out of 5 valence electrons bonds with the 4 electrons of silicon. The 5th electron of the dopant is set free. Thus, the impurity atom donates a free electron for conduction in the lattice and is called donor. Since the number of free electrons increases by the addition of an impurity, the negative charge carriers increase. Hence, it is called N-type semiconductor. When a pure silicon is doped with a trivalent impurity, then the 3 valence electrons of the impurity bonds with 3 of the 4 valence electrons of the silicon. This leaves a hole in the impurity. These impurity atoms which are ready to accept bonded electrons are called acceptors. With the increase in the number of impurities, holes are increased. Hence, it is called P-type semiconductor. When the N-type semiconductor and P-type semiconductor materials are first joined together, a very large density gradient exists between both sides of the p-n junction. The result is that some of the free electrons from the donor impurity atoms begin to migrate across this newly formed junction to fill up the holes in the p-type material, producing negative ions. However, because the electrons have moved across the p-n junction from the N-type silicon to the p-type silicon, they leave behind positively charged donor ions on the negative side, and now the holes from the acceptor impurity migrate across the junction in the opposite direction into the region where there are large numbers of free electrons. As a result, the charge density of the p-type along the junction is filled with negatively charged acceptor ions, and the charge density of the N-type along the junction becomes positive. This charge transfer of electrons and holes across the p-n junction is known as diffusion. This process continues back and forth until the number of electrons which have crossed the junction have a large enough electrical charge to repel or prevent any more charge carriers from crossing over the junction. Eventually a state of equilibrium will occur, producing a potential barrier zone around the area of the junction as the donor atoms repel the holes and the acceptor atoms repel the electrons. This area around the p-n junction is now called the depletion layer. As the N-type material has lost electrons and the p-type has lost holes, the N-type material has become positive with respect to the p-type. If a suitable positive voltage is applied between the two ends of the p-n junction, it can supply free electrons and holes with the extra energy they require to cross the junction as the width of the depletion layer around the p-n junction is decreased. By applying a negative voltage, result in the free charges being pulled away from the junction, resulting in the depletion layer width being increased. This has the effect of increasing or decreasing the effective resistance of the junction itself, allowing or blocking the flow of current through the diode's p-n junction. Then the depletion layer widens with an increase in the application of a reverse voltage and narrows with an increase in the application of a forward voltage.